In this video, we're going to do example 2 from your handout on percentage yield. So let's start off with this one here, which is example 2. Hydrogen and carbon monoxide can be produced by reacting methane, which you might call carbon tetrahydride if you're using the naming system in grade 11, with water vapor. If 1.61 grams of methane is combined with 2 grams of water, producing 0.50 grams of hydrogen, determine the percent yield. So firstly, let's write a balanced equation. And I think it's not balanced at this time. We need 6 H's here. So that's going to give 6 H's. The carbons are balanced. The oxygen's balanced. Then we're good. So we have 1, 1, 1, and 3. And we have to write out some information. So we know that we have our mass is 1.61 grams of methane. And then it's reacting with 2.0 grams of water. We're told that we have a mass of hydrogen produced. We're told that basically we did this lab and we produced 0.50 grams. So what is that called when we produce? We already produced it, we collected it. Right, that would be our actual yield. Actual yield is 0.50 grams. And we want to find the percent yield. That said, we need the theoretical yield, which is basically just using stoichiometry to find the mass of H2 that could theoretically be produced. So similar to the previous question, the main problem, though, is that we have 2 masses, so which one do we choose? So yes, this has become a limiting reactant problem as well. So we have an extra step here. So before we do anything, let's write down our molar masses for things. So molar masses for H2 is 2.02 grams per mole. Molar mass for H2O is 18.02 grams per mole. And that's just using the periodic table. And the molar mass of CH4 is so 12.01 plus 4.04. We get 16.05 grams per mole, just using the periodic table. And so we need to find the number of moles of each so we can compare them and figure out which one is the LR. So let me just find the number of moles first. So the moles of CH4 is equal to the mass over the molar mass, which is equal to 1.61 grams over the 16.05 grams per mole. And we can cross out grams and get moles. I'm just going to rewrite the same thing here, but for water, so the moles of water is going to be equal to the mass of the water in the question over the molar mass of the water, which is 2.00 grams over 18.02 grams per mole. And so we'll cancel that and get moles in the end. And let's go ahead and figure that out. So 1.61 divided by the molar mass of methane, which is 0.1003115526 moles. And then the other one is 2 divided by 18.02, and we get 0.1109877991 moles. So we have to find the limiting reactant. So this was all basically done. So let me put that here. So to find LR. I can do that using several methods. I think the easiest method would just be to compare them by dividing them by their coefficient. It's beautiful here because the coefficients are just 1 and 1. So we don't really have to divide them at this point by their coefficients. We just have to basically just choose whichever one is the smallest one, since they're already 1 and 1 here. It's a 1-to-1 ratio. Theoretically, if you had 0.1003 moles of CH4, that's how much H2O should be reacting because it's a 1-to-1 ratio. But notice you have more than that. You have 0.11. So you have more H2O than required. So we have more H2O than required, right? Because it's a 1-to-1 ratio, it should only be 0.1003. Therefore, this is the excess reactant. And then this will be the limiting reactant. It will run out faster. So our methane is the limiting reactant. And so we're going to use that limiting reactant to find the theoretical yield now. So everything else is the same. We can just kind of ignore water at this point, and we can find our theoretical yield. So use LR to find theoretical yield. I'm just going to call it TY, theoretical yield. And so what we can do is do a mole ratio between our limiting reactant, which is methane, and our product, which is hydrogen gas. So we have 1 CH4 for every 3 H2s. Our moles are 0.100311526 moles of CH4 times 3 moles of H2 over 1 mole of CH4. Cancel out mole and mole. So we can do a 0.100311526 times 3, and we get 0.300934578 moles of H2. Now, before we can actually get our theoretical yield, well, this is our theoretical yield as moles. Before we can do our percent yield, we need to find the theoretical yield as mass, because our actual yield is given to us as a mass as well. So you can only compare them really if they're on the same unit. So let's do this here. We'll do number 4. We'll find the mass of H2 produced as a theoretical yield is equal to the moles that we found times the molar mass, which is equal to 0.3009. And I'm not putting all the digits, but they're still in my calculator. Moles times 2.02 grams per mole. That cancels out. And we get 0.607887847 grams. So that is our theoretical yield. So theoretically, we should have got about 0.6 grams, but we only got 0.5 grams. And so, again, it could be that we didn't let the reaction happen to completion. Maybe we didn't collect the product properly. Maybe there were some impurities. Who knows? There was something that went wrong there, and we didn't get the maximum that we want to produce. So now we just have to calculate what the percent yield was. So let's just mark down that this is the theoretical yield. So our percent yield is going to be the actual over the theoretical times 100%. And so we have 0.50 grams over the 0.6078, so on and so forth grams. I didn't put all the digits, but they're all still in my calculator, times 100%. So 0.5 divided by that, we get, and then times 100. Don't forget 2 times 100. We get about 82.2520141%, which is approximately to the correct number of sig figs. So sig figs here, we have 3 sig figs, 3 sig figs, 2 sig figs is our smallest number of sig figs. So it needs to be 2 significant figures here. So let's go ahead and do that. So it's approximately, it rounds to 82%. So therefore, the percent yield is approximately 82%. That's to two significant figures. So notice it was very similar to the last question we did. The main difference is that we had to find the limiting reactant to find our theoretical yield, which we said was about 0.6 grams or so about 0.6 grams. And just remember that whenever you find your theoretical yield, which is, technically this is my theoretical yield, it does need to match the actual yield when you're doing the percent yield. So that's why we have to convert it into the mass first to do our percentage yield there. And so you can go ahead and try example 3. And then once you're done example 3, you can go ahead and do the problem in the video link over here. There's an answer key for that within the video. There will also be another video made so you can check your work for example 3.